We're now going to investigate this idea of integration, and we're going to start by solving a problem. How do we find the area under a curve? Now, if it's a straight line or something like that, it's quite easy because we can use formulas we know already, area of a triangle, trapezium, whatever the shape happens to be. But when it's not a known curve, like we don't know that's a semicircle or anything like that, how on earth can we find its area? So that's the problem we want to solve. So the best we can do to start off with is use shapes we know. So if I estimate it, and yes, it doesn't look like it's going to be a good estimate, but I'll use rectangles. We know how to find the area of a rectangle. So I'll split it up into two rectangles, but what I do know is the area under that curve will be less than the area of those two rectangles, which works out to be 9. But then I can create two other rectangles, which underestimate. In fact, the first rectangle there is actually a straight line. It hasn't got any area in it. So the blue ones are what we call the inner rectangles, the red ones are the outer rectangles, the overestimates, the underestimates. The area of the inner ones turns out to be 1, so we know the area is somewhere between 1 and 9, so the logical thing to do is average it, and we get an estimate of 5. Turns out the actual area is 4. It's close, but not real great. Okay, let's do it again. How can we improve it? Use more rectangles, because now the overestimate is not going to be as much. So I've now made it into 5 rectangles. There's the outer ones. Working out that area, I now know it's less than or equal to 5.76. The inner ones, the underestimates, will turn out to be 2.56. Average those. 4.16, getting closer. What the heck, let's do it again. Let's go with 10. Okay, here they all come. There's the 10 of them. That one, working out the area, we get 4.84 for the overestimates. The underestimates, and we get 3.24. Average down is getting real close, 4.04. So clearly, the more rectangles we draw, the better the estimate's going to be. In fact, to get an exact one, if it was possible, we'd want an infinite number of rectangles. This is where our idea of limits is going to come in handy. So all right, let's now just look at this random curve and investigate the one rectangle. So say I'm trying to find, well, it doesn't look like a rectangle at this stage, but that particular strip there. We're trying to find some function that will calculate the area. I'm just going to call it function A. So area C, or function C, is going to be the area from the origin to C, or the area under that. Area X then will be the area from the origin to where I've placed the X. So the area I'm interested in would be the difference between the two. So that's going to be our estimate. So there's our rectangle. I've made the top flat to make it look like a rectangle. But the width there is X minus C. The height would be whatever the function value is at that point. So it's approximately going to be X minus C times function X. I can rewrite that, because remember, we know what function X is. That was the equation of the curve. That's going to be this area function we're trying to find, minus area C over X minus C. It's actually starting to look familiar, because I could rewrite X. Instead of calling it X, I'm going to call it C plus whatever the width of the rectangle is, which I'll call H. So now it says area C plus H minus area C over H. Again, I'm hoping this is starting to look familiar. So as the width of the rectangle decreases, in other words, we get more and more rectangles, our estimate's going to get better and better and better. So as that width approaches 0, if it was possible to make them 0, that's when we'd have an infinite number of rectangles, which is what we want. That area is going to become exact. So I now know that function X is the limit as H approaches 0 of AC plus H minus AC all over H. Now we're almost there. Because what I'm going to do is I'm going to replace the C with the X, because if H is approaching 0, then C and X are the same thing. So I've now made an X on the right-hand side, and I hope you do recognise that. That was our first principles formula for the derivative. So what it turns out is the function, that curve, is the derivative of this area function that we're trying to find. So the equation of the curve becomes the derivative of the area function. We just now need to go backwards from the derivative and get the area function. And that's what we looked at before with primitive functions. So it turns out the area under some random curve y equals function x between x equals a and b. Now, watch the notation carefully and I'll explain it to you. The area becomes, and this is how we write it, that is the integral symbol. It is the letter S. Now, you might not recognise it. It's the long S, which they used to use back in the 1700s and what have you. You ever look at old textbooks and that, and you'll see it looks like, you think they're writing an F when you read it, but it's actually an S. And so that's what it is. It's S because that's standing for sum. You're summing all these rectangles. So there's the integral symbol, the function that we want to find the area under, which is function x, dx, so with respect to x, same as we saw with differentiation, is telling you which pronumeral are you working with. But then where are you going between? Well, I'm going between a and b, so we write that on either side of the s. The answer then would be function b minus function a, where that function is the primitive function. So where we go backwards, substituting b into that function minus substituting a, and you get the exact area. So let's now go and solve that one we just saw. It was y equals x cubed, and we were going from 0 to 2. So I would now write it like this. The area is the integral of x cubed going from 0 to 2. Our primitive function, when we're dealing with polynomials, add 1 to the power over that new power. So we've got a quarter x to the power of 4. You sub in the top one first, minus the bottom one, so 2 to the power of 4 minus 0 to the power of 4, and we get that answer that we saw before, 4 units squared. So it is an area, it needs units squared. And that is integration. So if I want to do something like this then, just like differentiation, we can do it term by term. So x squared, add 1 to the power over the power, I get a third x cubed. 1 would go back to x. Sub in the 3, sub in the 2, we end up with 22 on 3. Notice I didn't put any units, because now this is not an area question, this is just simply a mathematical operation. I'm finding the integral, so it comes up with a number as an answer. So make sure you know what it is that you're answering. Are they asking you to find an area, or are they just simply asking you what is the value of this mathematical expression? X to the negative 3, add 1 to the power over the power, it still works. So we get minus a half x to the minus 2. Now personally, I like to take that out of index form because I just find it easier to substitute in. So 1 over 5 squared, that's 1/25th, minus 1 over 4 squared, 1/16th. You get 9 over 800. I guess it depends on how good your calculator is. Some you can sub 5 to the power of negative 2 in and you get the exact answer straight away. Some you can't. So here's an interesting one. Differentiate, remember our notations for calculus? We said one way we could do it is say d, whatever we're going to differentiate dx. And that's what this is saying. We're going to differentiate this integral with respect to x. Well, let's first work out what that integral is so we know what it is we're differentiating. So it would integrate to be some primitive function. I don't know what it is, but some primitive function. I would substitute in x minus substitute in c, and that is what I'm differentiating. Now, think about it. If I differentiate the primitive function, then I'm back to where I started from, because they're opposite operations. But if I differentiate fc, I'm going to get 0, because I'm substituting in a constant number into this function. The answer would be a constant number. Differentiate a constant number, you get 0. So this just becomes function x minus 0, which is function x. So there's I don't know if you want to remember that formula or not. Function t to t, it really doesn't matter what's in there. That could have been function z to z, or function y to y, or function p to p. It doesn't matter, because you're going to be substituting into those pronumerals anyway. So the some people in some books you see them called dummy variables. I don't use that term myself, but you'll see it from time to time. There's our first bit of theory for the